In this video, we'll be taking a look at lattice energy. Lattice energy is the energy released by forming 1 mole of a solid salt from its constituent ions in the gas phase. For example, if we take 1 magnesium 2+ ion in the gas phase plus 2 Cl- ions in the gas phase, they will form 1 unit of MgCl2 solid, magnesium chloride. U is the energy change associated with this, the symbol for lattice energy, and it is minus 2,540 kilojoules per mole for magnesium chloride. This is quite exothermic. Larger lattice energies result from 2 factors. The first one is larger charges that cause a stronger electrostatic attraction between the ions. This is by far the dominant factor and the first one you should look for. Larger lattice energies also result from smaller ions because they can get closer together, and this causes stronger electrostatic attraction. But this is the minor factor. We determine these lattice energies through the Born-Haber cycle, and you can get a look at that through the linked video. Let's talk about a couple examples. Which salt has the larger lattice energy, lithium chloride or sodium chloride? Well, we need to look at the charges first. Here is an excerpt of the periodic table that you get on your exams. We can figure out what charges are going to be on these ions by looking at how far they have to jump, how many electrons they need to gain or lose in order to resemble a noble gas. Remember that noble gas electron configurations are full in their valence shells and therefore very stable. Well, both lithium and sodium are alkali metals. Both of them want to give up 1 electron each, meaning that lithium will resemble helium and sodium will resemble neon. Therefore, both of these will form +1 cations. Now, the chlorine, on the other hand, is over here in the halogens. Chlorine wants to gain 1 electron so that it can resemble argon. Recall that if you lose electrons, it's like jumping spaces to the left in the periodic table. Gaining electrons is like jumping spaces to the right in terms of electron configuration. So the sodium and the lithium will form +1 cations, and the chlorine will form a -1 anion. This makes sense since there's a 1-to-1 ratio of ions in both of these salts. So since both of these are +1 -1 salts, we must now consider ionic size. Here's our periodic table back again. Both of these salts have chlorine as the anion, so we only need to consider the cations, lithium and sodium. Recall from last semester that the atomic and ionic size increases as we move down a column in the table. Sodium is lower down than lithium, therefore lithium is the smaller species. And that applies to the cations as well. Li+ is smaller than Na+. So we've got +1 -1 salts, but the lithium plus is smaller. Since the charges are equal, the smaller lithium ion will cause the lithium chloride to have a stronger ionic attraction and therefore the larger lattice energy. Let's take a look at the actual values. Lithium chloride has a lattice energy of -894 kilojoules per mole, while sodium chloride has one of -786 kilojoules per mole. The lithium chloride value is more negative, therefore it has the larger lattice energy, as we would expect. Let's try one more example. Which salt has the larger lattice energy, lithium fluoride or magnesium oxide? Well, again, charges first. Here's our table. Lithium, we established in the last example, will have a +1 cation, but take a look at the magnesium. Magnesium is an alkaline earth. It needs to give up 2 electrons in order to reach a noble gas configuration. Therefore, magnesium will form a +2 cation. Fluorine is in our halogens, just like the chlorine. It's going to gain 1 electron, so it can look like neon. Oxygen, however, will have to gain 2 electrons to look like neon. So, in summary, our lithium will form a +1 cation, fluorine a -1 anion, magnesium a +2 cation, and oxygen a -2 anion. And these charges also balance out if you look at the formulas that were given. So, because magnesium oxide is a +2 - 2 salt, the larger charges mean it has the stronger ionic attraction and the larger lattice energy. We don't even need to consider size. Looking at the actual values, lithium fluoride's lattice energy is -1049 kilojoules per mole, and magnesium oxide's is -3791 kilojoules per mole. This is much, much, much more negative and a much larger lattice energy. Now let's also compare this to our previous example. We said that the lithium chloride has the larger lattice energy compared to sodium chloride. The difference when we have to consider species size is only about 100 kilojoules per mole, while the difference between charges is about 2,800 kilojoules per mole. This demonstrates that the charges have by far the stronger effect. Well, I hope that this answered a few of your questions. If not, feel free to come to my office hours or hit up a study pod. Otherwise, I will see you next class.